So the topic today is Rolle's theorem, mean value theorem. These are what I call existence theorems. They're not so practical as far as a lot of application comes from them, but they help us decide whether a certain conditions can exist or not. The only one you've had so far that's similar is the intermediate value theorem, which again, when we used it, you might have thought, well, it's not so earth-shattering or whatnot, and maybe didn't have the most application. But it could help you with your reasoning if you had to prove that something was the case or that something could, a scenario could exist or could not exist. And that's the same thing we're going to do today, but we're going to do it with tangents. It's very visual, so it'll make sense to you what they mean. But as I say, most of the time you're going to be using this for existence. So if you come across a question on your AP exam and it says, is it possible or could this happen? Those are asking you about existence. Intermediate value theorem, Rolle's and mean value theorem, those are the three go-tos in this class when you have to do that. So I'll show you what Rolle's theorem looks like. We'll see if you can figure it out. I always give this guy a hard time because when I think of, exactly what it takes to get a theorem in mathematics, right? To actually have your name beside a theorem, you think it has to be something very significant, right? Well, here's what I'm going to do. Okay, I'm going to start making my function, and I have to pass through those points. So, what do you think has to happen to the derivative? Good, so you've seen it. That's what Rolle would have seen as well, I suppose. That's the points I've chosen here. Somewhere in the middle there has to be a tangent line where it's also horizontal. See that? So you can kind of reason with yourself that if you were to go through the point and make it all the way to the other side, you have to come back down again. So somewhere in the middle there has to be a bump, right? A maximum like that. Now, how could you get around this? What are the conditions that Rolle's theorem has to have in order to apply? How could you get around it? Yeah. It has to be continuous for sure. Because if you just picked your, you could go like this and say, here's my graph. Haha. I didn't have to make that point, right? So it has to be continuous. Even more so than continuity, can you think of what else? I guess it should be a major hint that I said even more than continuity. Well, think about this. Okay. Is there a spot where the derivative equals 0 there? Yeah, it's supposed to be the absolute value graph. Apologies if my artistic skills don't show it well. But there is no spot where that graph is going to be equal to 0. How come? How could I get around it? What's unique about what I just drew? There's a corner, and so what does that mean? What's undefined? Yeah, derivative. So it's not defined. Okay? So it's not differentiable is what we would say. So for Rolle's theorem to apply, what we need to have here is f is differentiable inside an interval, so everywhere inside it, and continuous on the whole thing. So it has to exist at the endpoints as well. But basically we're saying everywhere you go in the middle, I should be able to make a tangent. It should be differentiable. And if it's differentiable everywhere in the middle, it's continuous in the middle. So really all we're saying is the endpoints have to exist. It has to be well behaved. If that's the case, there must be at least one point in the middle between a and b where the derivative equals 0. You might also see it written as c is an element, meaning somewhere in the middle of this interval. There has to be at least one. As long as those conditions are true, there has to be at least the 1 point. It could be more than one. It could be that, I go like this, and I have 1, 2, 3 places where the derivative equals 0. I don't even have to keep crossing above the axes. Like I could go, like that and have 1, 2, 3, 4, 5 times that I do it. But the point is, there must be at least one spot where this happens. Okay, so let's use Rolle's theorem. We can put this in our graphing calculator. Oops. So I'm putting in x to the 4 minus 2x squared. And all I'm going to do is look at the picture here. So this is the area I'm interested in is somewhere closer. I'll zoom in on that. So I'll make my window. It's probably fine if I go from like -3 to 3. I don't need to be that far zoomed out. Okay, but according to Rolle's theorem here, there's a spot somewhere between here and somewhere between here. There must be at least one critical point. So if I wanted to give some kind of guess, that's probably, -2 is going to do it, and 0. Somewhere between -2 and 0, there must be at least one critical point for those values, and somewhere between 0 and 2 as well, because that's where it's going to hit 0. I don't know if that's 1.5 or 2.5, what it is. But now that I know they're there, I know it's worth going to find them. So let's see what critical points come up in this graph. So a bit of review like yesterday. See if you can find the critical points that are guaranteed by Rolle's theorem here. So those are the 3 points where you should find your critical values at 0, 1, and -1. And that was what we saw here in the graphing calculator. I'll just bring it up again one more time. So here at 0, -1, and +1, that's the critical points. And as I say, the only time you'll really need to rely on the theorem is if you're trying to show that there must be one, but maybe you don't actually have to go and find it. One thing I do want to update here, this part actually is not necessary. As long as they're the same, for example, if I knew that this part was the same as this part, then somewhere in the middle, in order to get back to where I started, there must be that same horizontal tangent. So, sorry, just to clarify, I put an extra equal sign there, just to make sure you have it. But then Rolle's theorem is quickly going to disappear on us. This supersedes Rolle's theorem. It tells you everything Rolle's theorem does as well. However, Rolle's theorem, I believe, is handy in proving certain theorems that we would be using. So Rolle's theorem is a special case that is helpful. However, the mean value theorem is more general. So let me show you what the mean value theorem looks like. Let's say that I have a graph, and I realize that this is always the same graph that I draw, but anyway. Here's what the mean value theorem says. Let's pick any 2 points on this graph. So I'm going to pick maybe this one and this one, and I'll make a line with them. Now, can anybody see how we might be able to get something from this secant line and the tangent line? This one's a little tougher until you kind of get a chance to see it, but let me highlight something for you here. This slope, if I roughly wanted to find it, I can do better than that here. Good enough. Okay. that's the tangent line, which is the same as that secant line. Okay, so the mean value theorem is basically taking Rolle's theorem. You have to tilt your head, and you're tilting it, right? So if you were to just flatten this out, the mean value theorem says anywhere in between there, you must have the slope equal. So for example, I could also go on here. It just so happens there's another spot, I don't know, maybe right about there, where it's also parallel. So like Rolle's, there could be more than one place, but there must be at least one place where the tangent line is equal to the secant line, meaning the slope at one point is equal to the slope through the endpoints. Okay, so same conditions apply. Has to be differentiable, has to be continuous. So differentiable inside, and then continuous on the whole thing. And this is what we're saying is this is the slope at 2 points. It must be equal to the derivative at some point where C is somewhere in the middle of A and B. So for those of you who don't like the interval notation, I'm saying that C is between A and B. Okay, so this must be true. And again, this would apply to Rolle's theorem as well, because then when you calculated the slope of the 2 points, the slope between these 2 points is just 0. So there must be a spot where the derivative is 0. So it's like taking the Rolle's theorem is when you flatten out the mean value theorem. And mean value theorem lets you turn Rolle's theorem any angle you want, any slope that you want to use. Okay. So here's an example of finding the one guaranteed. So on the interval from 1 to 4, find all values where the derivative is equal to the slope between the 2 points. So what you should recognize here, this is a slope between 2 points. So let's go ahead and calculate it. I'm looking at the value at 1 and the value at 4. So this is the point 1, 1, and this is the point 4, 4. So the slope is going to be 4 minus 1 over 4 minus 1. So here's the slope that we're predicting. And mean value theorem says there must be at least one place where you'll find that slope tangent to the graph. So if I'm going to find it, I need to find the derivative. So it might help if you were to think about this as 5 minus 4 and x to the negative 1. So you can use your power rule. So 5 becomes a 0. Then I'm going to have 4x to the negative 2, or 4 over x squared. So if I want the derivative to be equal to 1, this is the value of the 2-point slope, this is the value of the derivative. What I'm saying is, where does the derivative have the same value? So x squared would have to be equal to 4, and x would be plus or minus 2. But in this case, I'm only interested in the positive one because it's only the values between 1 and 4 that are guaranteed by mean value theorem. So just 2 in this case. So let's take a look here. There's x equals 2, and I'll do my best to draw the tangent here. Oops. And if it doesn't look parallel, it's my artistic abilities that are failing you. Okay. But there is the point where the tangent equals the 2-point slope, the old slope from grades lower than lower than calculus, I guess. Okay. So, for example, existence as far as having to explain yourself. Here's an example where the mean value theorem applies. It's harder to find these examples for the mean value theorem because, as I say, they're generally used in mathematics to prove existence. So a trucker's handed a ticket at a toll booth because in 2 hours they went 159 miles, and the speed limit is 65 miles per hour. So how is that possible if you don't have a police officer with a radar gun saying, look, I can see that you went over the speed limit, right? How is it possible? Well, if you have 159 miles and you did that in 2 hours, so she traveled 0 miles at time 0, that's going to give you her average speed. So the average speed of this trucker was 79.5 miles per hour. And remember, the average speed, that is what the 2-point slope represents. This here is the average rate of change, and this here is the instant rate of change. So when a police officer is putting their radar gun on your car, they're finding what your instant velocity is, right? The mean value theorem says, well, if you average 79.5 miles an hour, somewhere in between your trip, you had to have been driving at least that fast, right? So maybe they went exactly 79.5 miles per hour the whole time, right? So speed didn't change. They're still speeding. Maybe they went faster than that. Maybe they went slower. But regardless, if they were going 79.5 miles as the average, somewhere in the middle, you're going to find that same slope. So that's how we could explain it. Even though we didn't have a police officer or a radar gun there, you had to have been traveling at least that fast at some point if your average speed was 79.5. Of course, if you're a good mathematician, you'd also say that speed is a continuous and differentiable function. You know, all those other bits of the existence that have to be there. But anyway, people will just laugh at you if you do, so never mind.